Okay, I'll start. The first thing I want to make a final decision. Maybe share.
Sir, I had a question about project.
Okay.
So we have almost completed it. What you wanted to know is how do we set the K for LTL model checking? What is the upper bound that we need to check for?
Correct.
In the paper,
Of
there
course,
are
that
some exponential
depends
bound,
on.
and the paper they give some exponential bound which takes a lot of time to verify.
I don't understand. So I guess then I will have to give some test examples too. So there are some bounds, okay, that are some simple function of recurrence diameter. So of course, see the bound that you have to set, it is a function of the kind of property that you verify.
Okay. Sir, if you are going to give an example, could you give it for microwave example?
Say that again. So you're
We have used
suggesting that
microwave oven example as a test example in our case.
yes, you could use the some simple things, to start with, just like I suggested for. There is this toy example with for LTL. Okay, so that you can use for simple testing. Yes, you could use microwave examples. For small examples like that,
Okay.
you can, by just inspecting, you can determine what the bound is, correct? Or if the properties are of the kind FG, GF, or GP, FP, or with some excess, you know how to do it. We already discussed what the bounds for those things are, which are, for example, for FGP, GFFP, it is recurrence diameter. So, and even for the mutual exclusion example, the kind of properties that we have done are all of fall into this category, either GP, FP, or FG. FG or G of F, correct? There are some liveness properties, okay, that you could try and verify. But these liveness properties, what would be interesting is, see, liveness properties. How will you verify liveness properties in the absence of fairness? Okay. Now, in LTL, you don't need any extra effort to verify that. You could verify just by putting the fairness constraint as a precondition. Okay. So of course, then your formula gets a little bit more complicated, and therefore you will have to think about what uh, the the bound ought to be. Okay. Um, so a simple answer to your question is, I think your question is a good one, and for all for whatever the example is, as long as the properties are admit simple recurrence diameter or some function of it with excess, you can determine what that thing is. Okay. And you can use that as the bound. Now, when you verify liveness properties, they are, even for mutual exclusion, for toy things, maybe you'll be able to verify it. For mutual exclusion, you'll have to make some assumptions about, you have to have a fairness constraint as a precondition. And since fairness constraints can be stated as LTL formulas, you can try doing doing that. Now, in the case of mutual exclusion and so on, since you know the total number of states, so the total number of states is always well, that is not always about. Okay, so it could be exponential in the thing. So it's just for those kind of complicated examples is where you will have an issue. Okay. So that since we have not covered, so there you will have to use. Okay, the answer is not very obvious. Okay, so so that's that brings up a thing. So at least for simple properties, on all those examples, for simple properties for which the bound can be expressed as a function of a recurrence bound, you can go ahead and then do it. Okay. So if you want to go beyond that, you will have to think a little bit more as to what the thing is. I don't have an answer right away. So I will think about some formulas that you can actually do, a little bit more complex formulas, and we can figure what those bounds are. Okay, or you verify those properties up to some large bound. Okay, without any claim of completeness. That's all. So as to do a testing. Does that answer your question to some extent?
Can you tell me what the question is?
Who is this?
Argadeep. I think I have a similar question, sir.
So the question was, how do you decide on the bounds? Okay,
in your partner, actually, he had the doubt. He had the same doubt, sir.
Yeah, he has the same doubt, huh?
Yes, because
he asked me the question, what the question was. So I was trying to, I think we were discussing things about, we were discussing about how to choose bounds, okay? And that depends on, my answer to that question is, what is the property that you're trying to verify? So for simple liveness, simple safety properties like GP and FP, you know what the bound is, okay? So you can either inspect the the example, the actual transition system for that you're using, compute the diameter or the recurrence diameter. Since computing the recurrence diameter is also an exercise, you could test it out. So for small examples, you can inspect and compute the diameter yourself. Okay? So for those things, you can use them as the bound. Now, then if you want to go to FG of P, GF of P, for that also recurrence diameter, as we discussed, serves as a bound. So for all simple properties, you can, that admits a recurrence diameter or some modifications of x's. If you have some embedded x's, you have to count the number of x's, and then you have a linear bound, as we discussed. So for all simple properties, you can, that admit those bounds, you can use them. Recurrence diameter or a function of a recurrence diameter, you can use them. Now, if you're testing it out on more complex examples, that is when, for which you don't know what the, what the bound, at least we haven't discussed all classes of the threshold. Then for that, what I'm suggesting is, for now, if you want to test it out for some large bound, okay? And and then see what happens. Okay, I'm fine with that. I might think and give you some examples with some known bounds for certain formula, just to make it interesting to test it. And if I give that, when I produce that, you can test it out. But for all the examples that you do for simple properties for which we have discussed bounds, so those class of properties for which we have discussed bounds, which are either recurrence diameter or a function, you can use them. For more complex properties, do test them out, but with some large bounds. Okay, so that will be adequate for me. Yeah. Does that answer your question?
Yeah, okay. So the bound that was given in the paper was mod of m times 2 to the power mod of f, where m is the size of the cryptic key structure and f is the size of the formula. So you were using that, but it was taking like a lot of time.
You were using an exponential bound.
Yeah.
Yeah, but you don't need to use exponential bounds for all kinds of properties. Okay.
Yeah, that's what.
The immediate question will be, what is the property? I mean, it's not it's unnecessary for you if I don't know what the kind of properties that you're testing are. So if it's GP, FP, FGP, GFP, you don't need to use an exponential.
Yeah. So if we'll test what the property is and then.
Yeah, and also it depends on what examples, what is the transition system you are testing it on. Even for exponential bounds, if the transition system is small, I mean the number of and the formula size is small, even the exponential thing. So probably your transition system was big, and then you were trying to.
We were doing it on the microwave, and we had a 5-6 formula, so it's like going to. It was above 100.
About 8 states or something like that, no?
Yeah. And then the exponential in 5 was big.
Yeah, this is, yeah. So, yeah, I have another question. So how are you, did you do some sharing optimization? Have you guys implemented? Or you don't do that? See, because that's also can impact your efficiency.
Can you repeat what you said?
No, what I'm saying is, are you using the sharing optimization in your implementation or not?
I think we're not using it.
Okay, because I wanted you guys to try that, okay, since it's a joint project and since there are, I mean, you should be using it. Otherwise, the size of the formula very soon gets very big. Huh? That can also be a reason. So even for small examples, even for the size of microwave example, even with exponential bound, you should be able to get it, okay? I mean, that's an experiment that is worthwhile doing, okay? So I was really hoping that you would do it. That the thing, I'm kind of not insisting, but it would be interesting, for you to extend yourself to do it, because after all, this is a joint project, and then you will have to go that extra mile, by doing some introducing new variables and equating them. You should try to see if that thing can get you a little bit more. Okay. In any case, that's since I have made that optional, it's up to you. Okay. Doing it, but whoever does that, would be nice. Okay. So is anybody doing that? Have tried sharing? No? Nobody? Yes? No? So maybe I'll call out. Argadeep said he hasn't tried. Diganta?
No, I mean, not yet. I'll try it.
I think this is a fairly simple thing. No? Or did you not understand what I...
No, I just not tried it yet. I think I'll try it. I'll be able to do it.
Yeah. Anyway, but this is a orthogonal issue, okay? I mean, it's orthogonal to what the bound that you would use. If you're just naively using some exponential bound, even for properties that admit tighter bounds, then that you should certainly not be doing, because we have discussed the class of formulas for which recurrence diameter or some linear function of that will suffice. So for those kinds of things, you should do it. Okay. Maybe in order to keep the thing in, I think I will make a list of formulas that of the kind that I want you to test it on, and then maybe you could do it. That may be the best thing. So, but as an additional thing, I was saying that maybe you should try implementing the optimization so that there, even with exponential bound, you should be able to push it for transition systems of the size of microwave. Okay, is my... So what are the examples? Okay, so also, so you all of you, most of you have been trying microwave, is it? You're not using the CTL examples. I mean, the examples that are suggested for testing your CTL model checker on, with corresponding LTL properties. Maybe you should try that too. Okay, so let's discuss. Yeah. So any yes. So what do you, when do you prefer? Say, I was thinking. So today's 19th. I might need one more class. That's all. So one more class just to wind up today's topic. 24th and 26th. So I was thinking to have the exam in the first week of December, okay? Say on December 2nd. Is that okay with you guys?
Yes, sir.
If it could have it a little later, it would be nice, because first I have another exam.
First you have an exam.
Yeah.
So I could do any day during that week, okay? I don't want to do, because for the SMT course, I'm doing December 14th. And yeah, so I guess it's okay to have either 4th, or we can do 8th.
4th would be nice for me.
4th would be better. So is 4th okay? So
I have an exam I have a take home that is currently scheduled from 1st to the 4th. So if it is after the 4th, maybe 5th, that would be nice.
I have a thing on the 5th and 6th.
7th?
Yeah, that would be nice as well.
Okay.
7th is...
So next week, then I will spend, yeah. Yes.
Could we do 8th if possible?
Okay. So I have everyone here, 1, 2, 3, 4, 5, except Who's missing? Someone is missing. Oh, Shivang is missing. So who's teaming with Shivang?
Me.
Me means give me the name because I can't see your face. Is it Rishikesh?
Yeah.
Yes?
Yes.
Okay. So yeah, can you check with him? I mean, anyway, I mean, if you make a decision today, it's decided. That's all. He has to make himself available. That's all. So then let's decide on December 8th. Okay, I think I want to do in the afternoon at 3 p.m. Is that okay?
Yeah, I'm fine with it.
Okay, fine.
Yeah, that is fine.
So have I shared my thing or not? Maybe not. Yeah. I didn't share.
So could you provide a sample paper?
Yeah. Sample paper. I'll just like, I promised for SMT, I'll put some sample problems. Huh? I will do that.
Okay.
By the way, but the classes will be over. Okay. So, next next Tuesday, Thursday, I want to take classes. After that, it'll be over. But next Tuesday, Thursday will be mostly kind of revision and so on. So maybe if I can, I'll try to put out some problems, on the 24th itself, and maybe you'll have before the 24th, so you can take a look at them and. Yeah, I don't want to make it take home because then the problems will be somewhat bigger. So it's all open, everything, but it'll be problems. So it's limited time. That's all. So it's 2 hours or 3 hours, depending upon how many problems I make. At most 3 hours, most likely 2 hours, maybe 2 to 3 hours. So you can solve it, and then at that time, at the end of the prescribed time, you just have to.
So what kind of problems would they be, like proof problems or based on understanding?
It will be mostly testing concepts on actual examples.
Okay.
And yeah, sometimes I'm thinking, and of course we haven't done a lot of proofs, but thinking of having maybe making some simple, couple of simple proofs. They could be that. And the questions, I mean, I can also have some concept-based questions, basic questions. But mostly it will be problem solving, okay? On examples.
So as far as the submission is concerned, is something like handwritten in pictures fine? Or
I think you can handwritten, scanned, scan it and then send it. That's what you will have to do.
okay.
So try to write it neatly, because obviously it's going to have to be like that. So write it on a piece of paper, and then scan it and send it. Yeah. Okay. So, yes, so this is kind of classical way of doing LTL model checking, okay? It is not, see, one thing that we have not discussed in the past, I have discussed things because I spent a lot more on actual symbolic model checking and then having you do things with both BDD and SAT and spend a lot of time in implementation. I did not get to discuss Buki automaton, the automata-based verification and at all. Now, if people, so I should have, okay, normally I do spend, you know, like 3 to 4 lectures on automata-based things. Now, I should say, since I've not done it, if people want to get that, you can take, you'll get some exposure to it if you took the automata, one of those automata verification thing, logic automata and thing that Praveen, Aishwarya, they discussed. But nonetheless, you should be aware that there is, you know, the automata-based verification approach. But this one, okay, this, and they, you know, for LTL model checking, they also use a Tableau-based thing when you're doing automata-based verification. Although we haven't not covered Buki automaton and various properties of Buki automaton and so on, still this Tableau-based method, I'm covering it in such a way without actually for you needing to get an exposure on Buki automaton. Okay? But since that gap is there, if you really want to complement yourself, I encourage you to take one of those automata-based verification courses so that you will also get that knowledge. Okay. So you basically what you do is, and this method is, unlike the bounded model checking method, does not require you to require you to give a bound, just like the CTL model checking ran until it reached a fixed point iteratively. You know, here also, you know, maybe you can view it as fixed point computation, but we don't view it like that. And you will see that there is kind of a similarity to automata. Okay, I mean, after all, transition system is like automata, you know, since it has runs and so on. It's just that there is no acceptance condition, you know, there. But the fairness condition can, in some sense, be considered as acceptance condition. That is where the link comes. Whenever you do things with fairness, that link is there. But nonetheless, this method is for LTL, unlike the bounded LTL that you're doing. It is able to do without actually requiring for you to specify any bound. So what you do here is you construct a Kripke model, that is a transition system, labeled transition system, T5, for any LTL formula file that you want to model check. The first step is to convert that into a Kripke structure. And this Kripke structure for phi is constructed so that it will also have some fairness conditions. Okay, the fair parts of T phi are precisely those that satisfy phi. Okay, it is defined. This Kripke structure for any given formula is defined such that the fair parts generated by this transition system that you construct are precisely those that satisfy the LTL formula phi. And that T phi, that Kripke model that we construct, is what is called the tableau for phi. what we express as fairness conditions are exactly, if you were to study Buki automaton, that is, they are, the fairness conditions are exactly that. You'll have to visit those states infinitely often. That's how fairness condition is stated, is exactly how Buki automaton does. All those parts in which certain states are visited infinitely often. That's what is Buki automaton. Okay, so in that sense, we are transition. The Kripke model with fairness conditions is almost equivalent to a Buki automaton. So I'm just giving you that connection. So, but here, the Tableau-based method, the first step is to construct a tableau for a given formula that you want to check. And T5 is constructed using, and the states of T5 you will see are constructed in terms of the subformulas, or actually more precisely, sets of subformulas of phi. We'll get into more details. Okay. Then, that's the first step. So to check if phi, on all parts originating from one of any of the initial states satisfied, this is the model checking problem. What you do is you construct the tableau for T naught of phi. That is for the negation of formula phi. And then you construct the product of your model M that you're checking the property in, and the tableau T naught phi. When you do that, this product is defined such that it'll generate the parts that this generates are the intersection of the set of parts of T naught phi and M. So in other words, informally, so the parts of this product transition system is, if it is not empty, then it will contain those parts that violate phi, okay? And that's what you actually check. And this has to be done for the fair parts in T naught phi. And that they have to be empty, okay? So, and this thing, once you construct this product machine, this checking of whether the parts are empty is actually like doing EG of true under the fairness conditions that is defined on T naught phi, which is kind of simply extended to the product machine also. So in this sense, once you construct the product, then checking this emptiness is like doing EG of true under the fairness condition, and you have to check if that the set of states that you get by doing EG of true, it will be exactly those states from which any path will be violating phi. It will be satisfying not phi. So in that sense, this Tableau method reduces LTL model checking on M through these steps to CTL model checking with fairness on the product, machine. Since you've already implemented CTL model checking with fairness, you can actually test this method out, okay? So once you can construct this T phi by hand or T naught phi by hand and do this product, and then you can just check this if it is empty, EG of true of F, or that is empty or not on your CTL model checker that you've already implemented. Okay.
So
Any
how do
questions?
I'm sorry.
Yeah.
So how do we set the fairness
You have to speak
conditions?
up. Okay, let me. I've reduced my.
Yeah, how do we set the fairness conditions for the product structure or the acceptance of the product?
Lots of details in here. I'm skipping. Okay, though all those details we will get. Okay, we will get to.
Okay.
So first, the fairness condition is defined on this T. Okay, it's the fair parts on T5, and on the product machine, as we'll see, any fair part, the fairness condition is whatever fairness condition is imposed on T by T is carried over, okay, to that product thing as well. Yeah. So the fairness condition is just on those. It'll have, as we'll see, the states of this product machine will be a cross product of these things. So it'll have first component will be from T, the second component will be from M. So it is just the fairness condition on the product machine is just extended to those parts in which the fairness condition of the first component on that product state has.
Okay.
That's how it's done. Yeah. So I don't want to get into all that. I mean, there'll be lots of formal definitions, etc. Okay, and examples that you will see. Yeah, that's yeah. So the biggest thing, is the constructing the product, etc. is fairly simple. How you do the Tableau construction is the main crux of the thing, and the correctness of this method is also is very much based on proving that the tableau that you construct indeed fairly implements, it corresponds, faithfully implements the LTL semantics formula. So the states are the states of Tableau. That is, Tableau is just the Kripke model for phi, okay, for a given formula, okay. The states are subsets of subformulas of phi. The intuition is, you have seen the LTL semantics, right? I don't have a slide. I mean, it is here, included here. And you know how the formal semantics of LTL is defined, okay? So it is defined as satisfaction of an arbitrary LTL formula by a path on an infinite path. And it is defined, the semantics is defined on any given formula phi in terms of some suffix of that path satisfying the subformulas of phi. So when the states in any transition system, or for that matter, even automata, they kind of remember some history, that you have seen up to a certain point. So each state, we pretty much, because the semantics of LTL says, whether a particular path satisfies a formula is expressed in terms of whether some suffix of that path is satisfied by a subformula of the original formula. So it is kind of intuitively clear that if you want to construct a Kripke model, that in some sense, corresponds to a phi, you will have to remember what the truth assignments for each of the subformula is. Okay, and that is why you make the states as not the various possible subsets of the original formula. Now, I don't know, you guys, most of you have had logic, haven't you, as a course? Is there anyone that has not formally taken the logic course taught by Praveen or Nakumar and so on here? Okay, so I guess all of you have. Now, if I don't know if Praveen covers something called the Herbrand model. Have you heard of Herbrand model for first order predicate calculus? Yes or no? Have anyone heard of Herbrand model?
No, sir.
No.
Okay, so that is not happened. But Kapil, have you taken the logic course under Praveen?
Yes, this sem.
Oh, you are taking it this term.
Yeah.
He doesn't cover Herbrand model.
No.
Okay. Okay, so if you have not heard, see, I mean, there are models for, you've seen in my SMT course, once you define logic, there are models, for it, okay, right? You define the model. So first order predicate calculus, also you can construct models. And the Herbrand model is constructed in such a way that the domain elements are constructed in terms of the terms. It's the syntactic terms, the legal terms belonging to the logic itself. That itself defines a domain, okay? So the model that Herbrand constructed for first order predicate calculus, the domain was not like, some arbitrary thing, so independent. So he tried to express it in terms of the terms themselves. So there is some kind of a parallel here, and I thought, I don't know if this parallel is drawn by everybody, but so this is a way of constructing it, the transition system starting from the formula structure itself. So there is a parallel to this Herbrand model construction. Okay? And so this transition system will indeed be a model exactly for that formula, because the parts in that precisely are the parts that satisfy phi. The transitions, number 2, transitions are defined such that for every state S and every formula that belongs to S, every path originating from S satisfies psi. Okay, that's how you define the transition system. You see now how the parallel between this and the how the semantics, LTL semantics is defined. Okay, so that's how it is. So we will define this construct, the tableau in these fashion. I mean, even before I give you the formal definition, here is a tableau for a simple LTL formula denoting a predicate P. Okay? So this is the initial state P. Once the initial state is a P state, after that you can either keep looping in a P state, go, and then you can loop forever in a not P state, or you could iterate between P and not P in arbitrary. So this is a possible, this is a tableau for P, because these transition systems, I mean, every part in this thing can exactly define the parts that are satisfied, infinite parts satisfying P. So, but you could, there are so many ways you can construct a tableau. For simple formulas, you can construct complete limitly, but this is more, this tableau construction here is more a systematic way of constructing. And even in literature, you will see it's a very automatic way of constructing. You can actually automate this process of construction. Okay? So it may not be the most optimal that it may not construct, but it will be complete and sound. So that's what, and it has to, the method has to work for arbitrary LTL formulas. Okay, so, and that's why in literature you will see a few variants of the way people construct tableau, and the compactness of the tableau construction by different people can vary. The one that I'm using is close to not the one that is presented in the textbook. Okay, I can give you a reference. I will upload this. Okay, and but I'm using the another book called Bayer and Katoven. Okay, and that is more geared towards Buki automaton, but the Tableau construction is that I'm presenting here in my slides are closer to the Bayer and Katoven method of constructing. Here's a tableau for X of A. So look at the states. There, the only subformula was P. And of course, you will have to consider P and not P also, as we will see, okay? So you'll have to keep track of both the subformulas and their negated versions. Now here's a tableau for XA. And, so XA, the subformulas are XA and XA. And as I said, we will also consider the negated. We keep track of the truth value for the negated version. So with that, we have 4 possible subsets of the set of all subformulas defined by the original formula XA. So this says that this is a state in which A has to be true and every path originating from XA has to be true. Okay, that's how you interpret that.
Sir,
Yes.
how this can be true that lower right node is there, right? From there is a transition from transition to lower left node, right? So how does this path satisfy not XA?
Yeah, what is not X?
Okay, sorry, mistake. That was mistake. Okay, I got it.
So not XA is in the next state, A should be false, no? So that's one. Yep. Yeah. Okay, so that's how it is constructed. So these transitions that you are defined so as to preserve the LTL semantics of the operators, the temporal operators that appear. Okay. Okay, any questions here? So I hope you're getting the idea of how. So this is the transition in consistency.
So there might be like multiple tableaus for a single formula, right?
That's correct. That is correct. So, but by, here I'll present a way, okay? So if you want to do it as though a machine can interpret it, you will consider all subsets. I mean, you can consider all subsets, all possible subsets, but you could optimize on them, by eliminating some obviously inconsistent ones and so on, and keeping it maximal so that you can construct, but then you would want to keep it such that it will be simple, more general. At the same time, the construction process, you should be able to prove that it is LTL semantics preserving, okay? I mean, the more optimization that you put in, the more, the harder it will be for you to prove formally that it is semantic preserving, yeah? It's almost like you're proving equivalence between 2 transition systems. So these are simple cases where you don't need any fairness conditions or anything. So fairness conditions will be required when you're dealing with the formulas that represent liveness property, okay, like the until operator. So here is the method that I say for constructing the states, okay? closure of phi is given a formula phi. A closure is the set of all subformulas of phi, including itself and its negated version. Okay, that is the closure. So, for example, closure of this formula phi here. So, by the way, we will restrict this tableau construction to predicates X and U operators. You know that the R and other R operator they are derived operators like F and G. They're all derived and they can be expressed in terms of until, and so you can so we won't be discussing explicitly what the tableau construction is for F, R, and G, as they can be expressed in terms of until. So you will have A, B, the negated versions. Not A and B is there, and therefore we have the negated version, and phi and not phi. Okay. Now, any subset of the closure, which are the ones that we'll be using to represent states, is elementary if it satisfies three conditions. It is propositionally consistent, that the propositional formulas that appear here have to be consistent with each other. It has to be maximal, and it has to be locally consistent with respect to the locally consistency is defined and with respect to the until operator. Okay? So S is propositionally consistent if for all phi 1 and phi 2 that psi belong to closure. Yes. Phi 1 and phi 2 belong to S, so should phi 1 and phi 2 individually. Okay? And if psi belongs to S, it cannot be the case that phi 1 and phi 2 belongs, but only phi 1. Because if something does not belong there in a subset, in a subset which we will be using to represent the states, so it will be considered as the negation being there. Okay. Yeah. So that's why if psi belongs to S, not psi cannot belong to S. That is, then it will be inconsistent. It's locally consistent. It makes sense only for you if for all formula of the kind phi 1 until phi 2 belonging to closure of F, if phi 2 belongs to S, if phi 2 belongs to S, which means phi 2 is true in S, then phi 1 until phi 2 must belong to S, because the semantics of until makes it true. No? So that's why you want, if phi 2 is in S, phi 1 until phi 2 should be in S. And if phi 1 until phi 2 is in S, but phi 2 is not in S, then phi 1 has to be in S. Otherwise, phi 1 until phi 2 will be false, correct? So that is the consistency as per the semantics of until operator. Correct? Okay, any questions? Okay. Now the third condition is that it has to be it has to be maximal. That is, if it is maximal, if it is full, in the sense, both either the positive version or the negative version of subformula has to be in each S. Okay. If psi is not in S, then not psi should be an S. In that sense, it has to be maximal. Now here there is an optimization that you could use. It is probably not necessary to keep, once you have all the literals in the set, the propositional terms like not A and B can be inferred. But this, so there is a further optimization probably you could do. But nonetheless, we will just keep that, at least in the examples that we have seen. So some examples. Suppose phi is A until not A and B. Is A an elementary set? Is the set containing A elementary as per the constraints?
No, right?
No, huh?
No.
Correct, because it's not maximal. Doesn't have, say anything about B. Nor, at least the way that we have, it doesn't have all the subformulas either. Okay, the positive and the negative version. How about the next?
It's not locally consistent.
No.
Oh, sorry, okay, it's locally consistent. Sorry. Yeah, okay.
We don't know because it is not even maximal. Therefore, I don't know. I mean, it doesn't even say if phi is in it or not. No? So if it is not maximal, you don't even know. I mean, the local consistency comes in once you include make it maximal. Okay. So how about this one? The next one? I haven't even thought about this. Okay. Phi, yeah. Phi is A until not A, B.
It's not consistent, is it?
Why not?
It has to be consistent. Shouldn't not A be in it?
Yeah. A and not A are conflicting. It's as simple as that. Okay. Yeah. So you're right. It is not consistent because both A and not A are in there, and therefore it is not consistent. Yeah. It's not. It's violating the propositional consistency requirement. Okay.
Yeah.
Yeah. How about the next one?
No, I think it's violating the local consistency.
Correct. Because since the phi2 part of phi is false, you'll have to have A to be true, but the state includes not A. Therefore, this is not elementary. Okay. Yeah, the next line, these are elementary. So I have a couple of instances where it is elementary. So phi is there. A, B, these are all propositionally consistent, isn't it? A and B being true means this is also true. And since phi is there and not of A is there, so that makes it phi. And oh, I have put the same thing, sorry. So the second one is the same thing I meant to do, use something else. Okay, so that's the, yeah. So by thing. So what you do is you're keeping it maximal. So which means that you are making all possible subsets, okay, and keeping it, and you're eliminating some of the inconsistent ones, or things that are violate the basic semantics of the until operator. Yeah. Yeah, so for any given, so for example here, The first part, this is just the definition. So you can eliminate. When you look at the formula, how do you actually construct the states? And then you have to eliminate. There may be better methods to generate all the states. I mean, one simple way is to list all the subformulas, make the table, and do it. And maybe there are better ways of generating if indeed you want to automate this method of construction. So here, just for illustration, I've constructed the all possible subsets, maximal subsets of the closure set, and then eliminated things that are that violate the thing. So so these three marked with X's, don't have to be included in the tableau. You should not include them in the tableau. That you have. Okay. See, when you have not a phi, where phi is an until operator, that also puts certain constraints. Okay, not a phi. So, I mean, it should not. The other components should be their truth value should be such that it should not be implying phi. Okay, because if not a phi is there, I mean, that means that not a phi is in it. Phi is not there, and therefore they should be consistent. They should not imply phi. Okay? So that also sometimes, like for example, here I've included not a phi in here. So then A and B cannot be there, because if it were there, then phi you would have to include phi, no? Therefore, that's why this is not locally consistent. Yeah. Yeah, this kind of is a very simple optimization, so that will eliminate some states from your thing. Otherwise, as you can see, this tableau construction is, the number of states is exponential. Okay, since you're taking all possible subsets. So in general, if you want to do it, that's why it is in the worst case exponential. This method, and there are some examples of LTL where the tableau is, the lower bound is exponential. Okay, so that's why that is one of the intuition behind this LTL model checking being p-space complete. Okay, so that is for states. So I'll go slow in this, okay, because there are lots of details here, and this I'll be probably taking part of next class as well, so I'll go slow. So now we have to define transitions, and that's where you have to define the transition. The states, the local consistency takes care of some aspects of the semantics preservation for phi, but then the real thing over path, the relationship between a formula and its subformula is has to be taken care of by the way that you define the transition of the tableau. Okay. So T phi in general has ST, the set of states, some set of initial states, RT, and its AP. And the AP is the closure, because every state is labeled with all the sum of the subformulas in the closure. Of course, I will get to the fairness constraint. I haven't included it yet. And then this set of states is this set of all elementary subsets of the formulas of the closure. And S naught, the initial state, is those states that include the original formula, the concerned formula of interest, yeah, that you're constructing the tableau for. So the transition relation is defined like this. And this, so first, if it includes an x psi, for every x psi that is in the closure, every subformula of the form x that has the next state operator, if it is say, then if x psi is in S, then the next state, its successor, should have psi in it, correct? Okay, that is because that is the temporal semantics of X. And for every subformula of the form that has an until operator that is in S, you remember the expansion law of phi1 until phi2. That's exactly how the semantics of phi1 until phi2, the satisfaction semantics on pi is defined. So it is equivalent to either phi2 is true right now, the current point, or phi1 has to be true. If not, then phi1 has to be true, and in the next state, you will have to have phi1 until phi2 to be true. This is kind of the recursive semantics of the until operator. And this transition is defined to preserve this expansion law. Okay, so it says that if phi2 belongs to the current state, then it doesn't matter. Okay, what the next state is could be anything. Okay, but if it is not, then you have to have phi1 in the current state, and phi1 until phi2 has to be in S prime, because you want phi1 until phi2 to be preserved for the entire path, because you're not sure if it is preserved right now in this at the current point. Okay, and that's how this thing is defined. Is that clear? Yeah. So is this clear? So this is exactly defining it in the to preserve the until semantics as per the expansion law. Now, if phi1, phi2 or does not belong to S, that is the negation of phi1 until phi2 belongs to S, then it is defined by taking the negation of it. That's all. Take the whole negation. Phi2 does not belong to S. I mean, yeah, phi1, if not a phi1 until phi2 belongs to S, then you have to take the negation. That is also implied by that, but I'm just explicitly stating it is. So then phi2 should not belong to S, and phi1, either phi1 does not belong to S, or or phi1, phi2 does not belong to S prime. Okay. Yeah. So that's how you define. So here is, for a moment, ignore the double circle on the state. For now, ignore it. Okay. So yeah. So as we saw, I've included these. Out of these 8, 3 are eliminated. The remaining 5 are included as the states here. Okay. This is the tableau. I'm illustrating the formal definition using the example of A until B. Yeah, so maybe I will illustrate this transition. A until A, not B, A until B. Yes, there has to be a transition to the next state. Phi2 does not belong to S. Therefore, the next, is phi1 indeed belongs to S. Therefore, phi1 until phi2, it will have a transition to all the states in which contain A until B. And that is B1 and B2. So in B1, you take the example of B1, then there it satisfies phi 2 of S, okay, because B belongs to that. So phi 2 is belonging to B1. Therefore, the second part doesn't even figure in. Therefore, means S prime can be, there is a transition to everything. That's why you will see there is a transition to itself, and there's a transition from that state to any of the, I mean, every other state, okay? And that's because, and you can see that, okay, that's how this definition is. Then once A until B is established, it becomes true, which is the case in B1 and B2. After that, it doesn't matter what follows it, it doesn't matter, okay? Anything can follow once A until B true. So that's how, well, that's the thing. And that's why you, you know, that's why it maps to everything, everything else. Okay, and you know, to see B5 transitions, you will have to use the negated version of this constraint, and that's what this thing is. So here, the negation is there, and therefore it'll have correct. Yeah, a transition to every, I mean, it'll have a transition only to the negated thing, so to itself and to that the negated version, and nothing and nothing else. So that's how you complete the transitions of the thing. Any questions here? Yeah, so if you have nested, so here I've used only one level of nesting to show it. So, but then if it is multiple level of nesting, you have multiple formulas, and then those transitions will be, you'll have to complete them by instantiating either of these rows. Okay, so if phi 1 and phi 2 happens to be some x of until and so on, you carry this recursively, and then you complete it. Okay. So does anyone, any of you see a problem with this? So firstly, do you understand how the transitions are defined? For phi 1 until phi 2, for x, you know, that is easy to understand. Yeah. So it's just follow these laws, that's all. So look at the transition, look at B3. So there is a self loop there. Because it is, so this is a state in which it is preserving it's locally consistent, yes, but it's not clear if eventually not B will ever hold good. Here it is fine. It is not violating A until B, but this depends on the future states, on the paths that are originating from here. So if you end up just infinitely staying in the same thing, then if you keep staying in B3 ad infinitum, then it'll violate A until B. That's the case, because A until B requires that eventually not B, there must be some point in the path originating from B3 at which not B has to hold good, okay? So for liveness properties, So you need to impose that condition, okay? And that's why you will have to see in the previous case, like for X, since X and P and so on, it didn't matter, everything could be there. There was no need for a fairness constraint. So whereas here, you have to get rid of certain parts. Otherwise, certain states, where you expect a liveness property to hold good, that eventuality might get violated due to this path being a little bit like this unfair. And that's why what you do is you put a fairness constraint that you should not be including these certain kinds of paths, okay? And that eliminates these kinds of eventuality thing. So T5 violates the following intended condition, that for every state S, every psi, every path originating from S has to satisfy because of certain liveness condition not being preserved. And therefore, this is fixed by attaching a fairness constraint, okay? That basically this is imposing the condition that this cannot be in my fairness. It cannot be a state in the fairness. So eventually either it has to be, the path originating from this has to infinitely often, visit a state that satisfies this condition. That is, eventually phi 2, it has to visit a state in which phi 2, the phi 2 here means B will hold good in this case. Or you can even have phi 1 until phi 2 negation of that also. It can also visit that state, okay? That's because once it visits this B, it is okay. After that, it doesn't matter. You can even visit negation, okay? The paths that where not of A until B holds is okay to occur, okay? And that's why for every subformula in the closure of phi, there is a fairness condition, okay? So that is F, okay? So it has, in this case, there's only one formula of the form phi 1 until phi 2, and therefore there is only one fairness condition, which just says you may not have B3 in, so it has to visit all the rest of the things as it is defined here infinitely often. Therefore, that eliminates this looping infinitely in B3 itself. Okay. Any questions? Okay. So then finally the initial conditions, all the states in which contain A until B have to be included, and therefore all B3, B1, and B2, they're all initial states. Since the negation is also included in the closure, so the tableau for the negation of A until B is very simple. All you need to do is to have the same fairness conditions and everything. You have to just flip the initial state, okay? So the tableau for not of F, that is not A until B, is the same as this, except the initial state becomes B4 and B5, okay? So it is fairly simple in that respect. Now I want to stop here, okay? And what I want you to do as an exercise for next class is, there'll be questions on this in the final exam, okay? So you might as well get the thing. So take an example of something like a nested formula, a simple nested formula, where phi1 and phi2 have x's, or x first do for that, and f something nested until, and c just one level of nesting, and try to simulate this and get a transition system for that. And if you get stuck anywhere and in the process, then you will have, and convince yourself that even for this thing, convince yourself, I haven't gone through all the things. You have to convince yourself that this is correct. In the sense, how do you convince yourself? You will have to see if every path originating from a state, for every formula that is included in the state is satisfied by every path originating from that state. Okay, and that's how this thing is defined. And that's what makes this guarantees the correctness. That is, that this will, every path originating from the initial state, then it satisfies the formula. So you first convince yourself by looking at this, and then for every state, and then I'm suggesting that you do by making it for one level of nested formula to construct. Okay, and
so could you provide reference to this?
Yeah. So what I can do is I'll post selected pages. Okay. The thing is that Katoan book here, this thing is discussed. I will give you that. Okay. But you will have to be aware. I'm giving you one warning that, see, ideally, I would have liked to have discussed the differences between Kroning's method of tableau construction and this one. But anyway, I'll give you selected pages from Katoan book. That is discussed in the context of Bookie automaton, okay? But you go through that anyway. So there will be some small syntactic differences between Bookie automaton, but I don't think it is going to be that hard. I will post immediately, Kapil, the pages. You go through that and then follow that, and then we can discuss, yeah? Even if you get confused because it is in the context of Bookie automaton, but you will see that there is, and if you kind of filter those details out, you can do. So I will post the relevant pages from the PDF thing, okay? And you can follow that. Yeah. So any other questions? Okay, I'll post these slides as well. Yep. Stop share.